Hey, what's up guys? Welcome to another Meta tutorial, and in this tutorial we are going to learn how to work with spaces in Meta. Specifically, we are going to learn how we can add atoms to spaces, how we can remove atoms to spaces, and also update atoms existing in spaces with new ones. So we're also going to see how we can create our own custom spaces, and along the way we will see how we can use the control flow structures let and let star. So they are ways of binding values to variables within expressions. More on that later on, but for now let's get started by seeing how we can create new spaces and add atoms, remove atoms, and also actually perform CRUD operations on spaces. So spaces in Meta are dynamic environments, meaning that we can add atoms, remove atoms, and basically perform CRUD operation on spaces as the program executes or at runtime. So so far we've been adding information to our space by using parentheses when declaring knowledge in this form. Say Dre is the parent of Zoe. This declaration of knowledge adds this bit of information to the space, to this one, the space referenced by self. So later on, if we want to query this information, all we need to do is write a pattern matching statement or expression. Sorry, it's an expression as such, and we simply get our output, or we query our space in this way. But what if we wanted to create our own space and add atoms and remove and update and so on and so forth? What we need to do is first create a space or a new space. To do this, we mainly need two functions, first of which is called the bind function, written with this exclamation mark at the end, and the new space function, which is used to create a new instance of a clean empty space instance. So what the bind function does is it binds the newly created instance of the space to a reference that we could later on use to reference to the newly created space. So the way it works is, first we write our bind statement. The bind function registers a token or a unique identifier with our newly created space. So the first argument is going to be the identifier. So let's say I want to name my identifier Smith family, because I'm going to store the Smith family's information into this space, and the next argument is going to be the new space function. Since this is an expression, I'm going to include it in parentheses. If I leave these parentheses out, then this would not be treated as an expression and Meta won't evaluate it, and so a new space will not be created. So I need to put it in parentheses. So yeah, if after creating this I want to match and see that this space is indeed empty, all I need to do is use this pattern matching statement, and when I execute I can see that it is empty because it does not output any information. So yeah, this is how we create spaces in Meta. So the next step is going to be adding a new member. To add atoms or knowledge to spaces, we make use of a function called addAtom. addAtom, written this way. This addAtom function accepts two arguments to it. The first is going to be the identifier of the space, or the reference, and the second argument is going to be the atom that we want to add, or the bit of information that we are adding to the referenced space. So it's that simple. So let's add an atom. Let's say addAtom and reference this SNET family space, and I want to add George is the parent of William. I want to add this bit of information, and also let's say that Martha is also a parent of William. Sorry. Okay. After doing this, if I do the pattern matching, I'm going to see that these new informations have been added to the Smith family space. So I get parent Martha William and parent George William. Cool. So this is how we add atoms or knowledge into a space that we want to add to. A quick side note over here, this first way of adding information to the self atom space, and I'm going to show you here now. This way, parent Ray Zoe, these are equivalent to each other. So just as a side note, they are equivalent ways of adding atoms to the self space. Okay, now let's move on to see how we can remove a member from, or a knowledge instance from, spaces. So we have a remove atom function. The remove atom function works in a way similar to addAtom. So it accepts as the first argument the reference of the space instance we want to use, so Smith family, and the second argument is going to be the pattern that we want to match against and remove from the space instance. So in this case, I'm going to attempt to remove parent Martha William from the Smith family space. So if I uncomment this and copy it here, then we're going to see the output of the two instances of the two Smith family space. So the first one is going to be parent Martha William, and the parent Martha William and parent George William, and the second one is going to be only parent George William. So we can see that it has been removed from the Smith family space. Okay, now that we have seen how we can remove and add new members, we can see next how we can update atoms. In MeTTa, there is no update atom function defined in the standard library, but we can use these two functions, remove atom and add atom, to implement our own update atom function by using the logic that first updating is just simply removing previous or old atom and adding a new one, a new instance of the atom. We can leverage this idea to implement our own update function. So we're going to see how we can do that, but before that I'm going to do a quick segue into control structures in MeTTa, or control flow in MeTTa. I want us to see the let and let star structures, since we are going to need the ability to temporarily bind values to variables, and that is what these two functions basically do for us. They enable us to temporarily store values on temporary variables within a scope of an expression. So let's see how they work. First, let's start by the let function. The let function is used to bind temporary variables to to bind temporary values to variables, and use those bounded variables into our own computations. You can imagine first binding an output of an expression being reduced, then using that as an input to another computation in your function definitions or whatever you want to do. Okay, so generally it is used to introduce variables and assign values to those variables, and afterwards use those variables to do some kind of computation. Okay, so let's see how we can use this to our advantage. Say I want to bind a variable x, and I want to the value I want to bind to it is 1 plus 2. So the first argument that the let function accepts is the variables that we want to introduce. The variables are going to be the first argument. Then the second argument is going to be the expression that is going to be reduced. So the value, basically the value we want to bind. Then the third is going to be the operation that we want to perform on the already bounded variable. So let's say I want to multiply the output x by 4. So what we expect from this expression is, first, x is going to be bounded to this reduced value 1 plus 2, that is going to be 3. Then afterwards, after binding it, we are going to perform this operation here, that is multiplied by 4, so we are going to get 12 as the output. And if I run it, as you can see, 12 gets logged onto our console. Okay, so this is how we use the let control flow. Then let's now see how we can use the let star and why we have to use it, and why do we use it basically. So we use let star in the case that when we are required to have several consecutive substitutions with variables. Say for instance, I have a variable x that is bounded to 1, and I want to use this x value and compute another value y from that x value. Say I want to add 1 to x. Again, this is a very simple example, and so on. I use x in another substitution, and so on and so on. So this is how I use how we realize this kind of consecutive substitution in MeTTa by using the let star definition. So the arguments to the let star function are going to be 2, the first of which is going to be a tuple of consecutive bindings. Let me just format it in a cleaner way. So the first one is going to be a tuple or a list of consecutive substitutions that we are performing, while the second argument is going to be the returned value after the successive computations being performed in the first argument. So let us just start by working this kind of relationship over here that I have written down as an example. So let us say x is going to be reduced to plus 1 2, and I want y to be an increment of x, so I say 1 plus x, sorry, here this needs to be a tuple, so it's going to look like this, since the first argument is going to be a tuple of subsequent substitutions between variables and values. This is the value and this is the variable. So the next one is going to look like this. X, so y is going to be 1 plus x, and I can continue on by adding z, and let's say I want to multiply y by 8, and as a final result, the result of this computation is going to be outputted on the second parameter of the argument of the let star function. So I'm going to say z here. So if I execute this, it should work properly, and I'm going to get 32. So I have first added 1 plus 2, which is 3, and incremented it by 1 and bound it to y, which makes y 4, and after that I multiply y by 8, and that results in 32. A quick note here, since this is not an expression resulting, this is not an expression, it's just a numeric value, I don't need to use parentheses here because it won't be reduced. So I would output z only, then I would get 32 with the curly brackets, not curly brackets but parentheses removed. But if I wanted to return an expression, say like 1 plus 10, 10 plus z, sorry, then I need to include these parentheses. So in MeTTa, you need to understand that if it's an expression that you are writing, then you must include it in parentheses. Otherwise, you don't need to use parentheses. You can just leave it as is. So yeah, now that we've seen how we can use the let and let star definitions, we can safely proceed to define our update function. So as is usual in defining functions, we need first to write this equals sign here, then the function proceeds. So update atom is going to be the name, and the arguments, I want the arguments to be, the first one is going to be the space reference. I want to pass to the space instance I want to update the atom from, so the space reference is going to be the first argument, and the second argument is going to be the old atom, and the third one is going to be the new atom. So let's use variables space old atom and new atom. So these are the values that are, rather the arguments that are passed to update atom. Now, like I've said earlier, all I need to do is first remove the old one and then add the new instance of the atom. So we need to pass the space first and the old atom to remove atom, and the next one is going to be add atom space and new atom. So this is not valid, this is not a valid code, so what I need to do is, this is not valid because I'm trying to execute two function calls within this function, and they are not enclosed in parentheses, like I've said before. If you want to write an expression that needs to be evaluated or reduced, you need to include it in parentheses. So yeah, but this is not also going to work right now. What I need to do first is use the remove atom function, and put it in a let function, a let statement, and let's bind the output of remove function on X, and paste back remove atom function call here. So now what I did is I first called the remove atom on the space, and all datum that I want to remove. Then afterwards, after I have bound the output of remove atom to X, I can proceed in this same expression to perform this one, the adding of the new atom to the space, to the same space. So new atom is added to the space after the old atom has been removed. Let me indent it so it is clearer to see. So this is how it looks, but now as you can see I have two parentheses. The outer parenthesis is not important since this whole expression is the let expression is already included in parentheses, so I can remove the outer ones and properly format it again, and there you have it. So we have defined the update function. Now we can use update atom function to update an existing atom. So let's do an example. So let's say I want to add an atom to Smith family, and I want that knowledge to be that William is 11 years old. So I want to say age William 11. This means the age of William is 11. So I've added this atom. Now what I want to do is update atom and update the age of William, basically using the update atom function to update the age of William to change it to 12. So what I need to do is first pass the space to the update atom function. So I would say family, Smith family, and the old atom I want to remove. So age William 11 is the old atom. William 11. The new age is going to be William 12. Now, after this operation, if I have successfully removed the old version of age William 11 and added the new version of age William 12, then the age of William is going to be 12, not 11. So I can simply pattern match against age William X, and I could say William is now X years old. So let's check our output. So as you can see, we have William is now 12 years old outputted into our console. So our update atom function works correctly. So yeah, this is how we could perform CRUD operations on spaces. So just to do a quick recap of this tutorial, we have seen how we can create spaces in MeTTa, and how we can add information to spaces by using the add atom function, and also by using the remove function that we can remove atoms from spaces, and also how we can implement an update function to to update existing instances of atoms from a given instance of a space. So I'll see you in the next tutorial. We have completed this tutorial.